there. And a sort of basic real analysis fact about a family of alpha Lipschitz functions is that if we have such a family that's uniformly bounded above on compacts, and we take the supremum, the pointwise supremum of that family, then the resulting pointwise supremum will be a function that is itself going to be alpha Lipschitz. This is the sort of thing that we teach in an introductory real analysis class. And so a consequence of that is that if we have a function that's bounded below on compacts and satisfies this growth condition at minus infinity and this growth condition at plus infinity, then there's going to be at least one alpha Lipschitz function that's less than f. And so we can consider the class of alpha Lipschitz functions that are dominated by f, that's non-empty, and we can take the pointwise supremum of that class, that non-empty class of functions, and that will be the unique greatest function from the reals of the reals that's dominated pointwise by f, and it'll be alpha Lipschitz. And we call that guy the alpha Lipschitz minorant of f. And that's the object that we're going to be interested in here, the greatest alpha Lipschitz function that's dominated by a particular function f of interest to us. And an associated object that's going to be of interest to us is the corresponding contact set that we'll call script z of f, which will be of interest to us when f is a Catlag function, is the set of points in time where f of t, or the right limit, the left limit f of t is equal to the value of its alpha Lipschitz minorant. So loosely speaking, it's the set of points in time where the graph of the alpha Lipschitz minorant touches the graph of f, loosely speaking. So here's a picture to give you a bit of an idea of what the alpha Lipschitz minorant of the graph, the alpha Lipschitz minorant of a particular, in this case, continuous function looks like. It's of course our an instance of our favorite continuous function, the path of a one-dimensional, of course, Brownian motion. We see that the alpha Lipschitz minorant is a function that has these kind of sawtooth paths that in between the points where it makes contact with the graph of the Brownian path has segments that are of this sawtooth form. It rises with slope alpha up to a local maximum and then decreases with slope minus alpha. And we'll see that that is typical behavior. So the first thing we need to point out is that it's not hard to give a recipe for finding what the minorant is. I mean, we've sort of shown this recipe for the minorant that we have to sort of, in principle, consider all the alpha Lipschitz functions dominated by our function f and take the pointwise supremum of those. But things aren't as complex as that. We can actually construct the value of m at t just by doing the following operation. And it's probably most easily explained by just looking at the picture here. We want to construct the value of the minorant at time t here. Well, what we do is take the tent function that has its peak centered at t, has slope alpha to the left of t, slope minus alpha to the right of t, and has height h. Okay, so that's what this function is here as a function of s. That's what that tent function looks like. And then what we do is lift that tent function up until, sort of start it with, sort of at h minus infinity, and lift it up until it first makes contact with the graph of f, and then that will be the value of m of t, the value of the minorant at t. And so this is how we will go about constructing m of t. And similarly, here we have the value of the minorant at time u constructed. We've taken the tent function centered at u with peak at time u and lifted it up until it first touches the graph of the function, and that's given us the value of the minorant at time u. And then just a little bit of reordering shows that this recipe here is nothing other than the same as this recipe here. Okay, that we fix t, and then just have to solve this optimization problem here to get the value of m of t. Okay, so it's just an easy optimization problem to solve to get the value of m of t. Okay, sorry for the dense slide here, but it just says what we see in this picture here about the sawtooth behavior. It says that if we've got a CAD-lag function with alpha Lipschitz minorant m, and the first thing it notes is that the contact set, the set where, loosely speaking, the minorant is the graph of the minorant touches the graph of the function, that set's closed. And then it says if we've got 2 times t prime and t double prime, such that at t prime, the graph is in touch with the minorant, and at t double prime, the graph is in touch with the minorant, and between t prime and t double prime, the graph of f is above the minorant. Then for t prime less than t double prime, so for t in between t prime and t double prime, what we have is that the minorant looks like a linear function with slope alpha up to some value t star, and then a linear function with slope minus alpha from t star up to t double prime, so that we have this sawtooth behavior in the complementary intervals to the contact set. And we want to have a nice recipe for constructing the first time after a given time that we're in the contact set. And of course, a recipe for doing that, we might as well consider the first time after zero that we're in the contact set. So let's let D be the first time greater than zero, such that we're in the contact set. And then let's define some auxiliary times S, which is the first time that this function here, first time greater than zero, that this function here is equal to the infimum of that function for values of u less than or equal to zero. So it's the first positive time that this guy attains its infimum over negative values. Okay, and then let's let E be the first time bigger than S that this function here attains its future infimum after times S. And then if we have that f of S is less than or equal to the left limit of f at S, this guy here, E, will actually turn out to be D. It'll actually turn out to be this first contact point. So I realize that that's a little bit to get one's head around. So I'll put it on a picture in the next slide. Here's our function f, and what it's saying is that we take a line of slope alpha and lift it up until it hits the graph of the path of f over times that are negative. Okay, so we lift it up until it hits this point here, right? Which we're assuming that the rest of the graph of f is somewhere sort of out here above this line here. So we've this is where the basically this infimum is achieved here. All right, and then we extend this line further in here and look at the first time where this line intersects the graph of our function f. Okay, and that's what this time s is here. Is the first time that the function ft min ft minus alpha t is less than or equal to that infimum over negative times, sorry. Okay, and then what we do is then look to the right of S and lift up a line of slope minus alpha and see where that line of slope minus alpha first intersects the graph of f to the right of S. And a little bit of work shows that if this condition here holds, that'll indeed be the first contact point of f with the minorant. Okay, I don't expect you to see that offhand. It sort of takes a little bit of thinking to actually conclude that. Okay, so now let's bring in something stochastic. So what we'll be interested in is the alpha Lipschitz minorant of a two-sided Lévy process. So what do we mean by that? Of course, what we just mean is a stochastic process X that takes the value 0 at 0 with Cadillac paths and stationary independent increments. Just from our observation about when the Lipschitz minorant of a deterministic function exists, it's not hard to see that the Lipschitz minorant of x will exist either almost surely or it won't exist almost surely, and it'll exist almost surely if and only if x has finite first moments and the absolute value of that first moment is less than alpha, excluding, of course, the trivial case when x is just the trivial drift out plus or minus alpha process. That is, the paths of x just look like a straight line with slope alpha or minus alpha. And so if you want to just fix on a particular example, just think of Brownian motion with drift beta, where the absolute value of beta is less than alpha. And let's let m of t be the alpha Lipschitz minorant of the Lévy process X. And we'll let script z be the contact set, and the random set z is stationary. Okay, it's distribution is shift invariant and it's regenerative. And I think this audience probably knows what I mean by regenerative. Certainly, if you've read Jean's monograph on subordinators, you know what this means. It means that if you have a stopping time that takes values in Z, then sort of the looking at the future of Z from that stopping time onwards is independent of the past. Okay, with a law that doesn't depend on where we stopped. And so fundamental fact in this business is that Z is going to be the closed range of a subordinator that, and of course we think normally of a subordinator as just a subset of the non-negative reals. And so we've taken such a set and made it stationary. So we've turned it into a subset of the reals that's a stationary subset of the reals. And that subordinator's unique up to a speed factor. Okay, and again, if we've read Jean's Lévy process book, we know that our Lévy process is characterized by its the Lévy-Hintschen description of its characteristic function. And so we have that when we look at its characteristic function, it has a Lévy-Hintschen exponent, and the Lévy-Hintschen exponent is of this form here, where A is in the reals, is sort of a drift term, a Brownian variance term, and a Lévy measure pi that satisfies the usual integrability condition. And if the paths of our Lévy process X have bounded variation, then that happens if and only if, of course, the Brownian term's 0, and we have this integrability condition on the Lévy measure. And in that case, the Lévy-Hintschen exponent can be rewritten like this, where we call D the drift coefficient. So a few facts about the contact set Z. Okay, just a general fact about regenerative sets. The random closed set Z either has infinite Lebesgue measure or 0 Lebesgue measure, almost surely. If the sample paths of X have unbounded variation, almost surely, then Z has 0 Lebesgue measure, almost surely. So just sort of a heuristic is that the rougher the paths of X are, the more spread out the contact set is. If X has sample paths of bounded variation of magnitude bigger than alpha, then Z has 0 Lebesgue measure, almost surely. If X has sample paths of bounded variation and drift less magnitude less than alpha, then Z has infinite Lebesgue measure almost surely. And if X has sample paths of bounded variation and the drifts has magnitude equal to alpha, then whether or not the Lebesgue measure of Z is infinite or zero is actually determined by an integral condition involving the Levy measure that I won't go into. So when's Z going to be discrete? So if Z has zero Lebesgue measure, then standard fact about regenerative sets, then Z is almost surely a discrete set, or almost surely a perfect set with empty interior. If the Brownian component is non-trivial, then Z is almost surely discrete. If the Brownian component is trivial and the Levy measure has infinite mass, then Z is almost surely discrete if and only if this integral here is finite. And if the Brownian component is trivial and the Levy measure is finite, then Z is almost surely discrete if and only if the drift term has magnitude greater than alpha. Okay, so now we'll move on to considering the second item here in the outline. So let's introduce a little bit of notation. For a time t, gt will be the last time before t that we're in the contact set, and dt will be the first time after t that we're in the contact set. And we'll just let G be G0 and D be D0. And just reminding you this construction that we had that worked for, that had nothing stochastic about it, that D was this infimum of times after this time S. So it was the first time that the process hit its ultimate infimum after S, where S is this stopping time, the first time that this guy here hit its infimum overall negative times. And of course, this works really well with Levy processes because when we subtract a linear drift off a Levy process, we get another Levy process. And so this works nicely with Levy processes, and this is just reminding you of the construction. And reminding you of another bit of terminology that you probably know is that we say that zero is regular for zero infinity for a Levy process y. If y immediately goes into the interval 0 infinity, for arbitrarily small positive times. So for example, 0 is regular for 0 infinity for Brownian motion with arbitrary drift, no matter what the drift is. And so it's a theorem that if xt plus alpha t is such that 0 is regular for 0 infinity, then if we look to the right of the first point in the contact set after 0, then that process is independent of the Lévy process up to that time. Okay, and moreover, this process here is Markovian with the same distribution as this guy here, conditioned to stay positive in the sense of a certain Doob H transform. Okay, and the random time D, oh, I've got it down here. Okay, this is certainly not an instance of the strong Markov property for X, right? Because this random time D involves looking into the future, right? Because it involves the future minima of the stochastic process X, or the stochastic process X with a drift attached to it. And so this is not just the strong Markov property for X. And so it's based on results from the 70s, most particularly from Warry Millar, that actually follow from more general results by Pittenger and Shi, or Gatur and Sharp about path decompositions at coterminal times. Okay, so now we'll move on to the third bit of the outline about so-called space-time regenerative systems. And so remember that dt is the first time to the right of the time t that we're in the contact set. And again, we'll have this assumption that the Lévy process xt plus alpha t, remember xt was a Lévy process, but xt plus alpha t is also a Lévy process. Suppose that this guy is such that 0 is regular for 0 infinity. Then no matter what t is, if we look at this guy here, we look at the future of X from dt onwards, subtracting off the value of X at dt. And then we look at the future of the contact set from dt onwards and shift everything back to the origin, right? So this set here is a subset of the non-negative reals, right? We've cut out z from dt onwards and then subtracted dt to get a subset of the positive reals. Turns out that this guy is independent of the past of xz up to the random time dt, and it has a distribution that doesn't depend on the time t. And let's sort of give a bit of a hint for why that's true. Well, it will depend on some properties of the Lipschitz-Minorant construction. First of all, if we've got a CAD-lag function and we just shift it in time and space and consider the minorant of the function f and the minorant of the function g, and the contact set of the function f and the contact set of the function g, then the minorant of g is just the space-time shift of the minorant of the function f, and the contact set of the function g is just the time shift of the contact set of the function f. I mean, this is pretty obvious, I think. And of course, we know, basic fact about Lévy processes. So to show the theorem, it's sufficient to show just the statement of the theorem with time t equals 0. Okay, the theorem was about general times t, and it's enough to show the statement of the theorem for time t equals 0. Okay, and then we have this thing that I call locality. And it says that if we've got a function for which the alpha Lipschitz minorant exists, and we're at a point A such that the minorant at A is equal to the value of the function at A. So in particular, we're in the contact set at A. We're in the contact set for f. And now let's define another function, f right arrow, which agrees with f for times bigger than a, but then for times less than or equal to a is just a line of slope alpha. So then what we have is that the alpha Lipschitz minorant of f right arrow, let's call that m right arrow. Then in fact we have that m of t is equal to m right arrow of t for all t greater than or equal to a. So in a sense, we don't need to look back before time a to be able to construct the Lipschitz minorant of f. So to prove the theorem, it suffices to recall that this recentered path here is independent of this piece of path here. And there's a corollary that says that if you work with a suitable filtration, this fact that we had for fixed times extends to stopping times in the suitable filtration. And I won't get into what that suitable filtration is, because we won't be sort of using it explicitly here. Okay, so what do we get out of that? Well, if the contact set is discrete, And we look at the successive points in the contacts set. Then the sequence of paths, which are the sort of, we can think of them as being the excursions away from the contact set. They're going to be independent and identically distributed sequence of paths as n varies. Okay, that's just going to actually sort of follow from this guy here. Okay, so you know, we sort of expect this now since we've shown the sort of requisite kind of independence that we need. So the successive excursions away from the contact set form a sequence of independent and identically distributed paths. Okay, when the contact set Z's not discrete, then we're sort of in the sort of setting that one would have for, say, excursions of Brownian motion away from its zero set, the sort of thing covered by Ito excursion theory. And there we can construct a Poisson random measure on the set R cross stopped paths that start at zero. And this guy records the excursions away from the contact set and the order in which they occur. Yeah, this is a you know, just exactly sort of what we'd expect. Okay, so now I want to finish up with looking at the case of Brownian motion with drift and do some explicit calculations. And first of all, need to remind you of Williams' decomposition from 1974. So this slide's written in sort of a little bit of a backwards way. So maybe let me start down at the bottom. So suppose mu is bigger than zero. And what Williams was interested in was a description of Brownian motion with drift mu that's positive in terms of the time and location of its global minimum. And the content of his path decomposition was that if you start the Brownian motion at zero, the height of the global minimum is minus gamma, where gamma is an exponential random variable with rate 2 mu. And if you look at the Brownian motion prior to it attaining its global minimum, that'll be a Brownian motion with drift minus mu. And so if we let tau be the first time that a Brownian motion with drift minus mu equals minus gamma, then we have that our Brownian motion with drift mu looks like that guy, the Brownian motion with drift minus mu, up to tau. And then we have to say how the Brownian motion with drift plus mu escapes its global minimum. And what it does is it escapes its global minimum looking like this. So it escapes the global minimum looking like a process like this, where RT mu is an independent diffusion that solves this SDE here, where B is an independent standard Brownian motion, independent of BT minus mu. Okay, so to build your Brownian motion with positive drift mu, you first run a Brownian motion with drift minus mu until it hits this level minus gamma, where gamma is exponential with rate 2 mu. And then after that, you follow this guy here that's been shifted down to level minus gamma. Okay. And just a little comment that this process R mu is usually called the three-dimensional Bessel process with drift because it's nothing other than the radial part of a three-dimensional Brownian motion with drift vector that's got magnitude mu. Okay, so from now on, the Lévy process that we're considering is a Brownian motion with drift beta, where the magnitude of beta is less than alpha, so xt is going to have an alpha Lipschitz minorant. And so by the Williams path decomposition, we know that the future of X after the first positive contact point with the Lipschitz minorant is nothing other than this. Of course, I probably should have a little D above here, as in, has the same distribution as, and where this process is a Bessel 3 with drift alpha plus beta. Okay, and let's write xt plus d minus d for 0 less than t less than zeta for the first positive time excursion away from the minorant. Okay, so in terms of the notation that we had before, d's t1 and zeta's t2 minus t1. And this first positive time excursion is the same as that of all the other excursions, except for the particular excursion that straddles time 0, right? That's the one that straddles 0 is particular, it's the usual Feller waiting time paradox. That's a particular one because we know it straddles 0. It's, special. It's got sort of some size biasing going on. And so we're interested in the distribution of the lifetime of this guy, the time L at which the minorant has its peak during the excursion, and the final value of the excursion. All right, so of course, since xd minus x sigma plus d is equal to m sigma plus d minus md. The final value of the excursion and the increment of the excursion and the final value of the increment of the minimum are the same. Okay, so there should be up here, I just didn't have room to put it in, sort of take a pair of random variables tau and gamma hat with this joint density and a standard Brownian excursion E on 0, 1 and a linear Brownian motion with drift this minus alpha plus b, and define a process frac E that looks like a Brownian rescaled version of E, the standard Brownian excursion with drift 2 alpha added to it, and then version of B tilde with shifted by 2 alpha t, so it started at 2 alpha t, and define this stopping time t tilde gamma alpha. So there's a lot going on, I realize, and the claim is that if we look at the excursion away, the excursion xt plus d minus xd, and then add on alpha t, then it'll be the same as ET. Okay, we found a path decomposition for this guy here. So the next slide shows that we have this Brownian excursion that's been rescaled. This should be a tau here, so it's a Brownian rescaling of a standard Brownian excursion. And then we have a Brownian motion with drift that's had a slope minus alpha added to it. I know that that's a lot to take in, but reading off from that, we can get explicit expressions for Laplace transforms, and in some cases densities of various things. So the lifetime of the first positive excursion, we can get the Laplace transform of that, and in particular when the drift parameter of the Brownian motion 0, we can get an explicit form of the density of the lifetime, where phi is the complementary Brownian CDF. The Laplace transform of the peak time, we can get an explicit formula for that, and an explicit formula for the density of the peak time, and the Laplace transform of the final value. We can get our hands on that. And the last thing that I wanted to mention is this has all been about the first excursion, positive excursion, which is the same as a generic excursion. And what about the excursion that straddles 0? Well, we have, by sort of analogs of general palm theory, formulae, the sort of size biasing type formula that says that if we're interested in some feature of the excursion straddling 0, then we can compute that in terms of stuff to do with the generic excursion just by doing an appropriate size biasing. That's coming from palm theory type observations. Okay, so thank you very much, and bon anniversaire, Jean.
Thank you. Questions?
Thank you, Stephen. Yes, I have a question about one of the results that you presented about your characterization when Z is a discrete set, almost surely, for the Levy processes. So you have an integral test which kind of resemble the one by Rogozin for regularity of or irregularity of 0 for the positive half line. And it's known that in the setting of a Rogozin theorem, you can also have a characterization directly in terms of the Levy measure. So my question is, you have a characterization which involves the one-dimensional distribution of your Levy process,
Aaron,
XT.
Can I show you something?
And is it possible to translate this into a condition on the Levy measure itself?
Oh, that would be great. Oh, am I muted? Am I muted?
No.
Oh, that would be great to know. Yeah, because we, if that is, because that's obviously much better to be able to do that. So we didn't see how to do that translation. So I'd love to know about that.
Okay, so this was really a question. Of course, no answer.
Yeah. So if you could, we sort of, sort of used sort of Rogozin stuff. Pat has a question there, which, that's something that we have no idea about the sort of a result which says you hand me the Levy characteristics of the Levy process, and I'll hand you back the Levy characteristics. So in other words, the drift and the Levy measure of the contact set. So no idea what are the possible characteristic, what are the possible subordinators for the contact set of the Minorand. Yeah, we thought about that and had no idea how to approach that.
Hi, Steve. Thank you for your talk. Can you hear me?
Yes, Takis.
Okay, so I just have a question because I know all this work about convex or concave majorands, minorands, and what is your motivation? Which, for me, it reminds me of the old paper of Spitzer and his approach to Wiener Hopf. What is the motivation for Lipschitz majorands? Is there any?
So the motivation was kind of sort of ex post, in that this is sort of subsequently become useful, and I should have mentioned this in terms of things to do with Berger's equation and Hamilton Jacobian, things like that. But sort of they aren't sort of really interested so much in these sample path type things. But this actual construction sort of appears there to be useful thinking about that. But that wasn't the motivation was just sheer curiosity.
Okay.
Because this was just seemed a natural thing to do after reading the convex Minorant type literature.
Mm-hmm. And does it make sense to start asking questions like Hölder majors or something? Or
yeah, I mean, you could do that, of course. Then the whole sort of it doesn't sort of play well then with the Lévy process structure, right? I mean, you know, you're not dealing with things that are piecewise linear anymore, and we looked at that, and it doesn't seem to look nice at all.
Yeah. Okay. Thank you.
Okay. Are there any? Yes. So Thomas has a question.
Hi, Steve. What happens when you vary alpha, and so maybe the excursion merged? Is it interesting or?
Yeah, you get. We have a paper about that. So, and this is sort of appropriate for this meeting. Jean has this concept of oh, I'm blanking now what he calls them, embedded regenerative sets. And so these guys, the sets are embedded in a very nice way. And so this is an instance of a sort of a whole continuum family of embedded regenerative sets.
Okay. So in the Brownian case, you have stuff like that. Okay. Or is it more general?
Oh, in more general, yeah.
Okay.
Yeah.
Okay. Thank you.
Other questions? Yes, in the chat.
May I ask a question?
Who is talking?
Me, on Mars.
Andreas. From March, no?
Yes, from Mars. So, Steve, I kind of missed the slide where you had you said it was indexed by R. So going backwards, I presume you pin the dual of the Lévy process going backwards into the negative times.
Yeah. The Lévy process is, you know, it's basically, you know, Lévy process with, you know, if you look at it from any point, you know, x t plus s minus x s plus t minus xs from any point onwards, any point s is, you know, a Lévy process on R, you know, a given Lévy process on R, right?
So well, actually, that's about part two of the question. Is, I mean, I'm not I think there's more than one way to define a levy process on R. I mean, there are versions. So I think what you mean is you just take the negative of the levy process.
Yeah.
Pin it at 0 and let it run into the negative.
Yeah.
So there are other versions you can take, depends on the levy process as well, I suppose. So there was some work of Paavo Salminen, I think ages ago. It was some kind of queuing paper where he constructed a subordinator coming from -infinity by using the stationary overshoot at zero. So you pin it. You pin a kind of dual version going back, and I think Jean used the same idea in another paper constructing with Nard and Salvov constructing self-similar processes entering at 0. So does that, I mean, that won't change anything in terms of the excursions, as you say. It's once you've pinned down the first contact point to the right, it's all the same, won't matter. But how would that change this excursion over the origin?
All right. So you want to do it in such a way that somehow you've made
I mean, it's a bit so gluing to levy process together is a little bit unnatural in a sense, because it means when you look forward from a negative value, you see it necessarily passing through a deterministic point at a deterministic time.
Yeah, but that doesn't have anything to do because that washes out with the
that washes out once
well.
you pass your first past the origin, right? Once you pass your first contact point past the origin.
Yeah, but no, the minorant, that's just a shift up and down in space, pinning it at 0, right? And so the subtracting off the minorant washes out. You know, if you know, naively, you could have started this guy with the value at 0 being distributed according to Lebesgue measure, right?
Right.
And then when you subtract off the minorant, you'd see the same thing, right? How you started the guy at 0 doesn't matter. It's the fact that you're looking at the guy that straddles 0. So you're dealing with the waiting time paradox. It's not the 0 in space that's killing you. It's the 0 in time that's killing you.
Okay, I've not formulated my question. Maybe I'll send you an email.
Okay.
But I agree that after your first, okay, anyway, I'll pass. I think Alex wants to ask a question.
Okay, so next question from Zoom.
Hi, am I audible? You can hear me? Probably,
Yeah, Alex.
Yeah, very good. Hi, Steve. Thank you very much for the talk. So maybe I missed something. I mean, all this is about the contact points. What about the set of these local maxima of the minorant? Is that, you can probably say something about that in the Brownian case, about its law or something like that. Is that true, or in the general Levy case?
Can you hear me? Yeah.
Yes.
Yeah. So sort of in principle, we, because the local maxima, in principle, we know those, you know, because we kind of know the contact times and the values at the values of the process at the contact times, and the peak is just a deterministic function of those. And so it's sort of given to you from data that you kind of already have your hands on. So you can say something about it. But say if you wanted to say something like, do the peaks form a regenerative set? That I wouldn't know the answer to just now, for example. The times of the peaks form a regenerative set. I wouldn't know the answer to that just now.
And it's also, I mean, it's not clear how to construct those times directly from the law of the process or something like that. As is, you know, in the convex minor case, that you have a nice description.
Right.
But here it's sort of the question of the entire excursion, probably.
Yeah.
The height, I mean, the local maximum and the time of the local maximum.
Yeah.
You need to know the entire trajectory. Yeah, thank you.
Sorry, Benedict, can I have another go at my question? Steve,
Yeah,
this is the point. So suppose you've got a levy process that doesn't hit points, and then you do your construction. And now I look at the excursion straddling the origin. So now I have an excursion so I have a path which necessarily hits 0. So it's more than just a straddled excursion. It's an excursion that's also conditioned to hit a point as well, right? Which you don't see in the Brownian setting because you hit points anyway.
But when you subtract off the minorant, you'd lose that.
So you lose the fact that because you don't know where the minorant is on the left.
Yeah.
Okay, thanks. I got there in the end.
Yeah.
Okay, thank you everybody for all these questions. I think that we can thank all the speakers of the day because the talks were really great. So thank you very much to all of you. So see you tomorrow morning at 9 for the next talks.